So I need to talk a little bit more about the log-partition function, um, because it has some interesting property. First of all, I can write a log-partition function like this, because remember that like this is the partition function is just the normalization factor, right? So again, like because like we have px is essentially just equal to exponential eta tx hx over exponential a eta, right? And of course this should normalize to 1, so if I take integral on both sides and take it should be, this side will be equal to 1, and so therefore I put this guy on the other side, then I have exponential a eta is this integral here, so I take the log, therefore I have a eta is equal to log this thing. And then like the interesting property of this log-partition function is that if we take the partial derivative of a eta with respect to a component of eta, let's say eta I, then what we observe is that like we will have something like this. So if we take partial derivative of that, partial derivative of log something will be just 1 over that argument, right? So I have 1 over this thing here, and then I take partial derivative of this guy here. Note that this transpose multiplied by this is essentially just summation of eta I t I x, right? Something, sum over I. So if I take partial derivative with eta I, so I will just have like tix coming out, so I have this one coming up. And note that again, like this thing here is actually a eta, and this thing here is actually our px, right? So therefore, like what we have is really this expression is just the expectation of tix. It's really nice. We take partial derivative of eta. With eta I, we just end up with the expectation of tix. And actually, we can even do further partial derivative on this log-partition function, and we can get a higher moment for the sufficient statistics. For example, if I take partial derivative of eta I and then eta j, go for some algebra, we will have something like that. This is essentially just the covariance between like tix and tjx.